All right, so here we have a mass on a spring, and it oscillates back and forth on a frictionless surface, so we don't have to worry about the work being done by that non-conservative force. The amplitude is given, okay, so that's our value of capital A. We're given the spring constant, and we're given the mass, although we'd have to change the units. So the question is to find the maximum speed of the object. Now recall, we've done this problem before. The maximum speed can be found by taking the amplitude and multiplying by the angular frequency. Okay, but we're not going to do that in this case. Again, that is a valid method of answering this question, but I want to look at it this from the point of view of energy. So what we can do is we can say that the energy at like the very far right-hand position, as far as it can travel to the right, will equal the energy in the middle, or at equilibrium. And when the object is all the way to the right, it's going to stop for a split second, so there would be no kinetic energy. It would all be in the form of potential energy, and specifically, it would be at its amplitude position. So I'm going to put in that capital A as my position. And then when it passes through equilibrium, it is moving at its maximum speed because all of the energy is in the form of kinetic energy. There is no energy stored in the spring. There's no 1/2 kx squared energy. And so I can notice that my 1/2s can cancel, make my calculation a little bit simpler. If I put in my value of little k and my amplitude in correct units, 0.04 meters squared, and my mass, divide by 1,000 there, so 0.05 kilograms, times my maximum speed, I will be able to find how fast the block is moving through the equilibrium point, which is its maximum speed. Not a huge number, I mean this is just a little block on a surface here, but 1.2 meters per second is that maximum speed. All right, question B asks to calculate the speed of the object when it is 2.5 centimeters from equilibrium. Okay, so at that point, it is not at either one of these positions. It's sort of in between. But I could take either one of these positions and look at the energy there, and that should, be the total energy. I'm going to start with the one that we already know, the 1/2 Ka squared, just in case I made a mistake with that speed calculation. So that would have to equal 1/2 kx squared, so some random position, plus 1/2 mv squared. Again, not the maximum speed, just the speed at this random position. I could again notice that there's a 1/2 in every term, so I can cancel those out. 0.45 times my amplitude, square that, that would equal 45 times this position. So it's 2.5 centimeters from equilibrium. Okay, so no need to subtract or anything. That is measured from equilibrium. That's our reference point. So 0.025. Sorry, I canceled out my 1/2. I'll put it back in there. And then the mass, again, is 0.05, and then times our speed squared. Now, before I calculate this, I certainly do expect this to be something less than 1.2, because some of the energy now is in the form of potential energy. It's not all kinetic, and so I expect there to be less of it remaining for the kinetic energy. All right, if I square root this here, so 0.94 is my speed, so I am getting something lower, so that makes sense. All right, so this would be a question that brings in some old ideas. So we have a bullet that is fired into this block, and then it's oscillating. I've switched to a bigger spring constant to handle this changing motion here. So the bullet has a mass of 10 grams fired into it. The first thing I'm asked to find is the period of the oscillation. So let's recall how you calculate the period of an oscillation. Certainly you could sort of find what omega is and that sort of thing, but the easiest way is to do something like this. T is equal to 2 pi, the square root of the mass that's on that spring. That's a lowercase k. So there's a number of masses in this problem. I gotta think about this. Initially, it's just a block of 50 grams, but then this bullet embeds in it, and they will move together. So the mass I should use would be both of those masses put together. So 60 grams or 0.06 kilograms. And then K is 2400. Right, and this comes out to be 0.031 seconds. Wow, that's fast, right? If you flip that over, you find the frequency. Just for your information, it's about 32 hertz, 32 times per second. This thing would be oscillating back and forth. What would be the amplitude of that oscillation? How big of a swing are we talking about? So the amplitude, that capital A, again, there's a number of ways that we can figure it out, but they all relate to the object of the spring, the mass on the spring, not directly to the bullet. So we're going to have to first sort of use some old ideas of momentum to analyze the collision between the bullet and the stationary block. So recall that if you know the initial momentum of a system, then you also know the final momentum of the system, with momentum being m times v. So we have a bullet of mass 10 traveling at 180, and it embeds in the block, so the total mass is 60 times v, and we find that our v is 30 meters per second. Notice I did not need to convert any units because of the symmetry of this setup. As long as my masses are in the same units and my speeds are the same units, it should work out. All right, so now what I know is that after the collision, the speed is 30 meters per second. Why is that important? That is going to be the maximum speed of the oscillation, because that's where the spring was relaxed. So that is the equilibrium point of the spring. And so now I know that maximum speed. And since I'm asked to find the amplitude, that would occur when the spring is compressed as much as possible. So that would be where there is no kinetic energy. So what we'll do is we can say that at the very beginning, or right after the collision, all of the energy is in the form of kinetic energy, the maximum speed. And then when it's pushed all the way as far as it can go at that moment in its motion, all of the energy would be in potential energy. I'm ignoring all the points in between. I'm just comparing these two moments so that I can find this unknown amplitude. My 1/2s cancel out. That happens often in these problems. The mass needs to be the total mass of everything that is oscillating, so that's the 0.06 kilograms. My speed is 30. Square that. I have this very strong spring, 2,400 newtons per meter, and that allows me to find my amplitude. And after I work through the algebra of solving this equation, I find that my amplitude is 0.15 meters or 15 centimeters, which does seem fairly reasonable.